Alright guys, so today we're going to be talking about projectile motion. And projectile motion is the movement of an object through the air along a curved path due to gravity. So those are the components that make a projectile motion. It's got to be in the air, meaning that hockey pucks along the surface of the ground do not count as projectile motion. And they have to have a curved path due to gravity. So gravity is going to be what's pulling down the object in order to give it that projectile motion. So some common examples that you come across are things like a hiker throwing a rock off of a mountain. The rock experiences a projectile motion because gravity is pulling it down and giving it that curve. Another example would be even a bullet that's shot directly horizontal, but since it's off of the ground and gravity is acting on it, it's going to experience a projectile motion. My favorite example is a sprinkler because you can actually see in real time the projectile motion. You see the whole path of the sprinkler perform a projectile motion. So I want to talk to you about the components of a projectile motion. And so we're going to use that sprinkler example again. And at time 0, when the water is first shot out of the sprinkler, is when the initial velocity it can be measured. And that water is also shot at an angle, and so we'll call that angle theta. We won't necessarily give it a measurement right now, but in knowing the initial velocity of the water being shot out of the sprinkler and the angle at which it was shot out in respect to the horizontal, then we can determine the two components of that velocity vector. And those two components are the horizontal, which we'll call velocity x because it's in the x-axis. We'll call that the horizontal component of the projectile motion, and the vertical component of the projectile motion, which we'll call vy. Now, with just that information, we can determine several different things about the projectile motion. Knowing vy, we can figure out the time that the projectile motion takes place. So how long is that projectile motion going to take place if we know the distance above the height? If we know the distance above the ground. So we can determine how long it's going to be in the air. Using the horizontal component of velocity, we can determine the range. So how far is it going to go? And there are other things that we can determine just from that. We can determine the peak height, so the max height that it will have. We can also determine velocities at different points of the projectile. And so that's just some things, and we're going to tackle that in the next video when we actually start calculating different aspects of projectile motion. But for now, I want to move on and talk a little bit more about those components of projectile motion and how they change throughout the projectile motion. And so just another example is, like, let's say a basketball. Let's say that I throw a basketball and there's no hoop here, so it's obvious that I'm playing basketball because I would totally miss it. And so we're playing basketball and we shoot the ball at an initial velocity, right, with a certain angle. And so we can determine from that the components, and that's what we have here is Vx and Vy. So those are the components of the projectile motion. And the first thing I want you to notice here is that the horizontal component of the projectile motion does not ever get any smaller or any bigger. Those are actually just copy and paste of the same thing, so they should be to scale. But they never get any smaller or any bigger, and that's because we ignore air resistance in the hypotheticals, and there's no net force acting on it to cause it to accelerate either up or down. And so it remains constant throughout the entire time. And then the second thing to notice is that the vertical component, the Vy, actually does change. And from the initial point here, from point 1 to point 2, it's gotten smaller. And then at point 3, at its peak height, it's equal to 0. And so the reason that is because you have a velocity upward in the positive direction, but the force acting on it, so think back to the definition, is gravity. Gravity is acting as the force on the ball, which is going to give it a acceleration in the downward direction. But your velocity is in the positive direction, and so that is going to cause the velocity to come down over time until eventually it reaches its peak height, and the velocity will equal 0. And then if we look over here on the other side of the projectile, we see that we once again picked up some velocity in the vertical component, but now it's in the downward direction, and we label it as negative. And so because gravity is still acting on it at this point in its projectile, it's going to continue accelerating it in a downward direction, but now we're going to go from, we went from positive to 0, and now we're going to start going into the negative. So now we call this a negative velocity. Velocity has a direction, so that's why we call it negative. If we were relating it to speed, which we'll talk about in this different video, speed remains constant throughout time because speed is a magnitude. But because the ball is coming down in the downward direction, we are referring to that as the negative direction, so we call it a negative velocity. Okay, and then another thing I want to show you about projectiles is that some of them, not all, can be really helpful because they will be symmetrical. So if I were to draw a straight line through here, because this is a symmetrical projectile motion, that I know that the distance covered here is equal to the distance covered here. And I also know that at 2.5 meters above the ground, the velocity in the vertical component is equal but opposite to the velocity in the vertical component on the other side of the projectile, also at 2.5 meters. The horizontal component, don't let yourself be tricked by a conceptual question like this. The horizontal component stays the same, stays positive throughout the entire time because there is no net force acting on the horizontal component. Okay, so now we're going to try a pretty elementary question, you could say, for projectile motion. We're going to tackle some harder problems throughout this playlist. But first, this question is asking us that tells us that a hiker throws a rock off. Okay. Now we're going to go ahead and tackle a problem in projectile motion, and this is more of an elementary problem, pretty straightforward. It wants us to find the vertical and horizontal components of a rock's projectile motion when it is thrown at an angle of 15 degrees at an initial speed of 5 meters per second. So we want to draw out that scenario, and we've got 5 meters per second at 15 degrees, and we were looking for the components of that projectile motion that we just talked about. So this is where we're going to use our trigonometry, and we got this little mnemonic, SOHCAHTOA. So if we wanted to use SO, where we'd be solving for the opposite leg of this right triangle, so we'd be solving for the vertical component of the initial velocity. And so we would do sine of 15 degrees is equal to the opposite over the hypotenuse, and our opposite is our vertical component, and our hypotenuse is the initial velocity, or our 5 meters per second, right? And so I don't have a calculator handy on me, but go ahead and solve for that, and you'll get the vertical component of the rock's initial speed. And then you would do the same approach for the horizontal component, except for you would be using cosine instead. You would use cosine of 15 degrees is equal to the adjacent over the hypotenuse, so adjacent being the horizontal component, the hypotenuse being, once again, 5 meters per second, and that way you would solve for the horizontal component of the initial speed of the rock being thrown off of the mountain. Okay? So that's just an initial problem. Another way that they could ask that question is they could give you the vertical and horizontal components and instead ask you to solve for the initial speed as well as the angle, and you would just use these same equations again. And if you guys have any questions, feel free to ask them in the comments below. We'll gladly answer as soon as possible. Thank you guys for watching.